Exercise 32. In this one we are given this set R, which as you can see has these integers as its elements. Now there are two operations also imposed on this set. One is addition modulo 10 and the other one is multiplication modulo 10. We have to prove that under these two things R is in fact a field. So let us draw or construct the composition tables for these two operations on R. So we do it first for the addition modulo 10 operation and then the multiplication one we will do. So there are how many? 5 elements. So we will need 6 rows and 6 columns. Okay, so let's now write the elements 0, 2, 4, 6, 8. 0, 2, 4, 6, 8. So this is the composition table for addition modulo 10. So 0 of course will not have any effect on the sum. I mean when we take the sum of say 0 and 2. So we are going to get these things. And because addition modulo n, I mean 10, of course the modulus is 10 here. The general one is addition modulo n, but now we have addition modulo 10. So that operation we already know is commutative. So from these entries we can automatically say that these entries also are the same. That's because 0 plus 2 is 2, so 2 plus 0 is also 2, like that. So once you have, you can now see why. Once you have the upper triangular part of this table, imagining this as the diagonal of the table, you get two parts which are triangular. One is this upper triangular part and the other one is the lower triangular part. Because of this commutative nature of the operation, it's enough to only find out the upper triangular entries because the lower triangle is then automatically determined. Next, 2 plus 2 is 4, and when you divide 4 by 10, the remainder is 4 because that's actually the answer of your 2 plus 2. When this class is not ordinary plus but addition modulo 10. Of course, in this case we do not see anything new, but it just seems like it's ordinary addition, but its effect you will see here. So 2 plus 2 is 4, 2 plus 4 is 6, 2 plus 6 is 8, but in this one 2 plus 10, had this been ordinary addition, you would have had 10 itself. But because we are dealing with addition modulo 10, this is 0. So we have 0. Again, because we have 6, 8, 0, so here also we have 6, 8, 0. The lower triangular part corresponding to these cells, they are automatically also determined. Then just like that, 4 plus 4 is 8. 4 plus 6 is 10, that means 0. 4 plus 8 is 12, that means 2. When you divide 12 by 10, the remainder is 2. And in fact, because your modulus is 10, it's especially easy to determine what the remainder is. You see, ordinary addition gives you 10. So when you are trying to calculate modulo 10, the remainder is just the last digit due to the nature of the modulus that it is 10. Had your modulus been 100, the remainder would have been the last 2 digits, like that. So then 0, 2, 0, 2, so 0, 2. 6 plus 6 is 12. 12 means 2. 6 plus 8 is 14. 14 means 4. So 4, and finally 8 plus 8 is 16. 16 means 6. So this is the full composition table for addition modulo 10 on this set. Now from this table, what is it that we see? So we are now going to write something about this table. From the above composition table for the operation addition modulo 10, the first thing we see is that the set R is closed under this operation. That's the first thing we see. And we already know some properties that this type of operations have, namely they are commutative, they are associative, and when two such operations are involved, say addition modulo n and multiplication modulo n, the distributive laws are also true. So we are going to use that prior knowledge of these things here. Addition modulo 10, we see that the set R is closed under it. Also, we know that addition modulo 10 is a commutative and associative operation. Fine. What else is true that we can see from this table? We can of course instantly see that 0 acts as an additive identity. The element 0 in R acts as an additive identity, or if you feel a little weird about saying additive identity, although the in the name addition modulo 10 we have addition, but still if you feel that we should not really write additive identity because we have not yet touched the operation multiplication. So as yet addition modulo 10 is just simply an operation. Okay, if you are just simply given an operation, then you may not want to call it addition. So in that case, you just simply say the element 0 acts as an identity element for the operation addition modulo 10. Like that also you can say. But anyway, we are just writing like this. So the element 0 acts as an additive identity. The additive, here also additive inverses we are going to write, but if you do not want to write it like that, you can just write the inverses of the elements, that is these elements under addition modulo 10 are these. The additive inverses are, let me, of course, I am not going to get rid of the table now itself. So let me just write from here. R. What's the additive inverse of 0? 0 itself, because it's the identity with respect to this addition, so it will be its own inverse. Okay, now what is 2? From the table we see that when we add 2 and 8, then we get 0. So that means the inverse of 2 under addition modulo 10 is 8. What about 4? The inverse of 4 is 6, and hence the inverse of 6 is 4, and the inverse of 8 is 2. So these are these respectively. So what we have managed to show is that R is an abelian group under addition modulo 10. Let's mention that. R is an abelian group Okay, next we okay, because I am writing these things and not just simply saying these things verbally, that means I am writing actually not a hint but the solution itself. So if you really are writing a solution, you should start with some verbs like this. Consider the following composition table for addition modulo 10. Okay, because of lack of space I am unable to write it fully, but you understand. So now we are going to do a similar thing for multiplication. Next, we consider the following composition table for multiplication modulo 10. Now I hope I have space for the table. Let me just here itself just roughly gauge how much space I will need. Okay, so this time multiplication modulo 10. The elements are the same, 0, 2, 4, 6 and 8. So the row for 0 will of course just be 0. All the entries will be 0. So the column will also be 0. Next, 2 times 2 is 4. So modulo 10, that is again just 4. 4 times 2 is 8. 2 times 6 is 12. So that means 2. 2 times 8 is 16. So that amounts to 6. So 8 to 6. 4 times 4 is 16. So 6. 4 times 6 is 24. That means 4. The last digit. This is 32. So 2. Then that means this is also 4, 2. And keep in mind that we are doing it similarly, just like that one, because like addition modulo 10, multiplication modulo 10 is also a commutative operation. Then 6 times 6 is 36. So 6, 48, 8, and finally 8 times 8 is 64. So 4. So here also we can see that our set R is closed under this operation also, multiplication mod 10. So the next things we are going to write, they are going to be similar. Once we have written this, before drawing the table, these things, this line, we do not need to repeat it again. We can just simply write from the above table, because now we know what the operation is. We see that R is closed under multiplication mod 12. Sorry, I said mod 12, mod 10. Next, we know that this operation, just like addition mod 10, is commutative and associative. But there is something else also. Multiplication modulo 10 is commutative, associative, and distributive over addition modulo 12, modulo 10. I don't know why I am saying 12 again and again. Okay, so we now have closure of R under this operation. The operation is commutative, the operation is associative, and also it is distributive over addition modulo 10. So this is where the two operations get linked to each other in the distributive law. So now what are the remaining things that we need to show in order to finally conclude that the system is a field? We still need a multiplicative identity, or in other words a unity in this ring. Note that we have already mentioned all the axioms for a ring. We have an abelian rule and we have a multiplication under which the set, the underlying set is closed, the multiplication is associative, and the distributive laws are true. And there is something else also, the multiplication is commutative. So in fact now at this very stage we can say that the system is in fact a commutative ring. But other things are also true, and now we need to see how. So we now need a unity in this ring, and we also need to show that non-zero elements have inverses under multiplication mod 10. If we manage to show these two things, then we can of course conclude that this is a field. But what is the unity here? The unity should be an element such that when you multiply any element with that element, nothing changes. You get that any element back. Do you see that with any of these elements? What about 6? You see that in the row labeled by 6, actually nothing has changed. 6 times 0 is 0, 6 times 2 is 2, 6 times 4 is 4, 6 times 6 is 6, and 6 times 8 is 8. So 6 is actually the unit element. In a general ring, just simply looking at a row is not enough. You have to also look at the column, but in this case that's not needed because our operation is commutative. Okay, in general you have to see both the things. From the table we see that, okay, before writing this, shall we conclude that this is the commutative? I think it will be a nice idea to do that. Instead of verifying say 10 or 11 axioms and then at once concluding that it's a field, I think it's much better to do the, what can I say, you do the conclusions in steps successively. First you have an abelian rule, then you have a commutative ring, and then you have a field. So here we conclude, hence R is a commutative ring when you write the actual solution. Of course you do not have to, you are writing it in some notebook or something like that, right? So It may seem a little strange that I'm keeping this and then writing somewhere else, but I'm keeping these things only for us to see so that we do not lose it. Hence, R is a commutative ring, and that's just it. That's the conclusion at this stage. Now we notice from the table above table, it does not really look like the above table, but rather from the table below, but that's not the point here. You see, ideally we are just going on writing things in their natural order. So from that point of view, it's justified we write now from the above table. We see that 6 is the unity in R. So that is one thing. And now we need to also see inverses of the non-zero element under this operation. So what will the inverse of 2 be? Something such that when you multiply 2 by that something, with that something, you get 6. And that you can see from here is 8. 2 times 8 is 6. 6 because that is our unity. And the inverses of 2, 4 and 6 and 8 are not again mentioning that under multiplication mod 10 because that's the operation we now have. The addition modulo 10 part is over. R. So 2 and 8. Oh, sorry. What am I writing? The inverse of 2 is 8. The inverse of 4 you can see is 4 itself because 4 times 4 is 6. And the inverse of 6 of course is just 6 because 6 is anyway the unit element, unity. So inverse of 4 is itself, inverse of 6 is itself, and inverse of 2 is 8, so inverse of 8 is 2. Respectively. Hence, R is a field under the given operations, and this is where the exercise ends. I mean the solution ends. Next, formulate the appropriate definition of a subdomain. And that is a sub-integral domain. Okay, just like we have the notion of a subgroup of a group, so like that, a subdomain of an integral domain. Let D be an integral domain with unity 1. Unity 1. What's the point of mentioning that the integral domain is with unity 1? Because in this text, integral domains by definition always have unity. Whereas that is not the case in Herstein's topics in algebra. In this text, an integral domain is a commutative ring with unity which has no zero divisor. Whereas in Herstein's topics in algebra, an integral domain is just a commutative ring with no zero divisor, and there the definition of zero divisor is also a little different from what we have here. Anyway, so this is the thing. Let D be an integral domain with unity 1. Okay, the symbol 1 represents the unit element. Show that P, which is equal to n dot 1, where n is any integer, is a subdomain of D. You understand what n dot 1 is. We have this thing in the beginning of this chapter on rings. In the beginning of this ring theory part. N dot 1 is 1 plus 1 plus 1 n times, taking the sum of n number of ones when n is a positive integer. 0.1 is by definition the zero element in the ring, and if n is negative, then n dot 1 has this meaning. Because n is negative, minus n is positive, and minus n dot 1 means 1 plus 1 plus 1 minus n times, and this minus indicates the fact that we are taking the additive inverse of that sum as an element in the ring. So that's the meaning of n dot 1. Or instead of saying all these things, we can just simply interpret n dot 1 as 1 to the power n. In this group, because our integral domain D is after all a ring, so with under the addition that it has, it's an abelian group. In that abelian group, if you imagine this element 1, it is some element in this group, so you can then consider its integral power 1 to the power n, where the exponent n is an integer, where this integral power has its usual meaning. Now that usual meaning reduces to, in this case because the operation is addition, to just these things. So these n dot 1s are nothing but integral powers of the element 1 in the additive group D. Okay, so that's the meaning. Okay, now, so let us continue. Let's first finish writing the exercise statement. We have to prove that this P is a subdomain of D. Oh, here within brackets something else is also written, that is all integral multiples of 1, that is understood, no need to write that separately. Additionally, show that P is contained in every subdomain of D. And further, there is something else also. What can you say about the order of P? That is, how many elements will there be in P? What can you say about that number? So we have three parts in this exercise. We have to first of all define an appropriate, we must first have an appropriate definition of a subdomain. Then under that definition, we have to prove that this P is a subdomain of D. Okay, so there are four things. Nah? Then we have to prove that any subdomain of D contains P inside of it. And then we have to say something about how many elements there are in P, that is the order of P. Okay, so let us start. You can imagine that the definition of a subdomain will be extremely straightforward. It is itself a domain which is just a subset of D. Solution. We define a subdomain of D to be a subset of D which is itself an integral domain under the operations in D, and which, let us just mention this also in order to be more clear about everything, and which has one, namely the unity in D, also as its own unity. Okay, so this is our definition of a subdomain. Now we need to prove that this P is a subdomain. Okay. So to prove that P is a subdomain, first of all, okay, so by this definition, what does it mean? What do we have to do? We have to prove that P is itself an integral domain under the operations that we have in D. So first of all, before anything else, P itself has to be a ring under the operations in D. That means P needs to be a subring of D. So let us first show that. Note that P is a non-empty subset of D. And by the way, how exactly is it a subset? Do you see how? That's because what are the elements in P? The elements in P look like this. That is, you understand that in the additive group D, it's the integral power 1 to the power n. Now, because D is a group and 1 is itself in D, so by your closure property and inverses everything, by the rules of exponents that are already there at our disposal from group theory, this type of things, all of them will belong to D. No matter what the exponent n is, that is, it can be any integer, still these things will be in D, and that's why P is a subset of D. And non-emptiness, of course, is evident because we are just simply having this n run over the entire set of integers. Okay, so that's how P is a non-empty subset of D. Now let us apply the subring test on P. So you recall that a non-empty subset will be a subring of D if when you take two elements, say A and B, from that set, their difference A minus B and their product AB are both again in that subset. So now we need to do that for P. So taking two elements from P means having two elements of the form, say n dot 1 and m dot 1, where n and m are integers. So that's how we are going to now take things. Let n dot 1 and m dot 1 belong to P, where of course n and m are arbitrary integers. Then by some previous exercises, I am not going to mention which one, maybe exercise 15 from the previous set of exercises. You can just go back and see which one. Then n dot 1 minus m dot 1. Okay, for this one we do not need any exercise. This is equal to n minus m dot 1, and that of course again belongs to P. What is this equation? Do you see? If you interpret this in the additive group D plus, then the equation will look like this. Because here n dot 1 is the nth power of 1 in this group, m dot 1 is the mth power of 1 in this group, and this minus represents inverse, additive inverse of course, but after all inverse in this group. And in between them we of course have the binary operation in the group. So that means in its place, what are we writing? We are writing this. Is it true? Yes, it is true, and it is an application of one of the rules of exponents that you already know is true in this group. So that's why we can just simply write without mentioning anything more this equation, and it's true. And for this we do not need anything else. But in the next one, where we are going to take the product of these two, there we are going to need one of the exercises, which of course also we have already seen and we have solved also. Okay, so that's the thing happening here. And so this is what I was talking about. When you take the product of these two things, you in fact get nm dot 1 1, actually 1 1, because in general you can have arbitrary elements a and b. So in that case you would have ab, Here however you have the same thing 1 1 which ultimately becomes 1. So you get this belongs to P. So here ideally I should mention which exercise from before we are using here, but I won't do that. So by the subring test, P is a subring of D. Okay, now because P is a subring of D and D being an integral domain lacks zero divisors, so there cannot be any zero divisor in P as well, because otherwise that zero divisor would be a zero divisor in D, contradicting its integral domain nature. So we write accordingly, since D is an integral domain, it is something else is also there that also we need to mention. It is commutative and lacks zero divisors. Consequently, P is also commutative. And lacks zero divisors. Fine. Is there anything else? Yeah. Of course, we also have to show that the unity in D, that is 1, is in P, but that is evident from the definition of P itself. Also, note that 1 belongs to P. How? You see, 1 belongs to P because this may look a little strange, but 1.1, you need to understand that in this 1.1, this one is something and this one is something else. I think in this form it will look somewhat confusing, so let me just simply write 1 suffix D. What this 1D represents is that it is the unity in the integral domain D, which may not be the actual integer 1. Here however it is actually 1, the integer 1 itself. And from the definition of these things, this is nothing but 1D itself, that is the integral domain unity element itself. And because this 1D is of this form, so it will naturally belong to P by the definition of P. So that's what we have written here. Also note that 1 belongs to P. So now we have all the pieces together. Now we can say hence P is a subdomain of D. Hence P is a subdomain of D. So we have finished 2 things. What are the other things that we have to? Okay, so the next one is we have to prove that any subdomain of D contains P inside of it. So in that sense, P is the smallest subdomain of D. So for that one, let K be a subdomain of P. Then the unity of D is in K, because K is a subdomain, so by definition it should contain the unity in D. Thus, now K being a subdomain is a subgroup of D under addition, and hence n times 1, n dot 1 will belong to K for any integer n, proving that P is a subset of K. Okay, shall we phrase it this way? Instead of writing thus, let me just write things. K is a subgroup of D under addition. This implies n dot 1 belongs to K for all integers n. Hence, P is a subset of K. So, any subdomain K contains P. And now finally, the final part asks us to say something about the order of P. The order of P. What is the order of P? P is a set. The order of P is the number of elements in P. Okay. Now, do you see one thing? What are the things that we have in P? In P, we have the integral powers of the unity as an element in P. All the integral powers, where the exponent can be negative integers also. Fine. Now, if 1 as an element in this additive group has infinite order, that is, as a group element, the element 1 has infinite order, then this P cannot be finite. Why? Because since 1 has infinite order, this equation 1 to the power m equal to the identity in this group, okay, in this group, that means 0, this equation is never true for a positive integer m. In other words, once you start considering all the powers of 1, all of them will belong to D, no doubt about that, but they are all distinct, okay. And why is that so? That is because if some of them is not say you have repetitions in this list, what will you then get? Let me just mess this place up a little bit. You will then get 1 to the power I equal to 1 to the power j for some integers, positive integers I and j. In fact, I can be 0 also. I am just simply saying for some integers I and j's, that is fine. This. But keep in mind that now you are in a group. So in a group you can just simply play with this equation and you will get, it will look extremely weird, but still from the group theoretic point of view it's a legitimate calculation. 0 is equal to 1 to the power j minus I. So what we have done is that we have multiplied on both sides by 1 to the power minus I, which we can do in a group because we are in a group, keep that in mind, and this is an additive group. So if you do that, then you will get the identity of the group on the left side, which is 0. On the right side you have 1 to the power j times 1 to the power minus I. So there you use one of the rules of exponents. So you get this, okay. But because of these inequalities, j minus I is a positive integer, and this fact is then violated. If j minus I is a positive integer, then that just tells you that such powers actually become identities. So one such smallest exponent is also there, for which the corresponding power would be the identity, implying that one has finite order, which contradicts your supposition that one does not have finite order. So that means if one has infinite order as a group element in this group, then this list has no repetition. But all of these things by definition are in P, so then P would be infinite, okay. However, when one is in fact an element in this group of finite order, then P would also be finite, and as you can probably see why, the order of P will be equal to the order of 1 in this group. However, the order of 1 in this group, whether it is finite or infinite, has a name. It's the characteristic of the integral domain D. That's what it is called in ring theory. So what we have in fact seen in all these things is that the order of P is equal to the characteristic of the integral domain. And we know from a previous result that every integral domain has two types of characteristics. I mean, okay, I should not say exactly that. There are two possibilities from among, there is exactly one from among these two possibilities. I was unable to frame the sentence properly. Characteristic of D is either 0, which is when one has infinite order as an element in this additive group of D, or the characteristic of D is a finite positive integer, which is when one has finite order as an element in this group D. And when it has a finite value, in this case of course it has finite value, but when it has a positive integral value, that value is a prime number. We have already proved these things. So let's just now write all the things neatly. Whatever we are going to write next, this is the last part of this solution, will be brief and neat. And if you want explanation, those explanations are here, what I said just now. And we are not going to repeat them here in the solution because these are things we have already seen previously. This is why you first study group theory and then you go to ring theory. Not that it has to be absolutely done all the time, but this is the natural way of going for these things, because a ring is also a group, an additive group. Note that the order of P is equal to the characteristic of D. So when the characteristic of D is 0, then of course the order, but then we cannot say it like this. No? Note that this, when, in general this is not true, this when characteristic of D is finite, and is a prime number. I think it's not called finite, but characteristic of D is positive. And hence a prime number. On the other hand, when characteristic of D is equal to 0, P is infinite, with no further explanations provided. So that's the solution. Let's solve one more. Prove that there is no integral domain with exactly 6 elements. At first glance it seems like a strange fact, but it is a fact nonetheless. Can your argument be adapted to show that there is no integral? I am losing ink. Let me just refill. There is no integral domain with exactly 4 elements, and then there is more. What about 15 elements? Use these observations to suggest a result. to suggest a result about what? About the number of elements in a finite integral domain. Okay. I won't write a formal solution, and I in fact doubt that I have in fact even written one full formal solution anywhere among these Gallian exercises, whether it be ring theory problems or group theory problems. So most of them, or I think almost all of them, are somehow incomplete, and that is deliberately so that you actually write the full solution for yourself. So here I am just going to go through the argument and let's see what happens. Say D is an integral domain for which actually there are 6 elements in D. Okay. Now you consider this fact. This is a group because after all D is a ring, so it's a group under its own addition. Do you see how much we are using group theory? So from a result on group theory, which is one of the corollaries to Lagrange's theorem, we next have this. Six dot x is equal to 0 for all x belonging to D. It is that corollary which tells us that say you have a group, a finite group whose order is n, say, then for any element x in G, the nth power of x is equal to the identity element in the group for all x in G. We are using this corollary to this additive group. Of course, in this additive group, and we have 6 in place of n now. For this additive group, x to the power 6 looks like this, 6 dot x, where this 6 dot x has that meaning which we have seen in the previous one, and that is equal to the identity element of this group, that is 0. Okay. So characteristic of D. Okay, characteristic of D divides 6. Why is that so? You can easily prove this by using the fact that the characteristic of D is the smallest positive integer which, when it exists, k, such that k dot x is equal to 0 for all x belonging to D. And you use the smallest nature of k also, you will see that if you apply the division algorithm to divide 6 by k, say you will have something like this, no? Where r is the remainder when you divide by k. So what will you get? Am I saying it correctly? Characteristic of D divides 6. Yeah, because it's the smallest. Yeah, this is how you should proceed, and you will be able to show that R is equal to 0. I won't tell you exactly how, but this is something we have already seen in group theory also. So because R is 0, this K should divide 6. The minimal nature of K will force R to be 0. Otherwise, you would get another such thing R, for which R dot x is also equal to 0 for all x belonging to D. And the minimal nature of K would then contradict that fact if you assume that R is greater than 0. Okay, so that's how you can prove that the characteristic of D divides 6. So there are exactly 4 possibilities here. So that means characteristic of D is either 1 or 2 or 3 or 6. Okay, just from this divisibility relation we have these possibilities. However, D is a finite integral domain, and we already have proved in one of the theorems that we see in the section or in this chapter that this characteristic in fact has to be a prime number. So that's why the characteristic of D either has to be equal to 2 or it has to be equal to 3. It can not be 1 or 6. Now if you suppose that the characteristic of D is 2, then what is it? Then you are having the fact that 2 dot x is equal to 0 for all x belonging to D from the definition of characteristic. However, because 3 divides 6, which is the order of this group, and remember that it's an abelian group because we are in a ring. So by Cauchy's theorem for abelian groups, there will exist an element y in D such that y is not equal to 0, but its cube is equal to 0. Its cube is the identity, which when we translate into our language, 3 dot y is equal to 0. Okay, such an element can be found, and it comes from Cauchy's theorem for abelian groups, which in general says that if you have a finite group G and a prime number divides the order of the group, then there will be at least one element x, or say y because we are taking y here, in G such that y is not equal to the identity element in G and y to the power p is equal to the identity element in G. In this case, p is 3, y is of course y, and e is 0. At the same time, because of this thing, you also have 2 dot y equal to 0. But using these two equations and the laws of exponents, you will be able to show that y is equal to 0, which will directly contradict this. And this is coming from the supposition that characteristic of D is 2. But if you assume instead this one, if you suppose that this one is the case, then a similar thing would happen, because in that case 3 dot x will be equal to 0 for all x. But because 2 also divides 6 just like 3, again by Cauchy's theorem for abelian groups, you would get an element of order 2 in your group. That is, you would get some z not equal to 0 in D such that 2 dot z is equal to 0. But because of this equation being true for in every element x in D, it's in particular true for z also. From there also similarly you will be able to show that z is 0 and simultaneously non-zero, a contradiction. So that is why this initial supposition itself is not true. So there can never be a finite integral domain with exactly 6 elements. Do you see the role played by these 2 and 3? And one more thing is that in order to be able to apply Cauchy's theorem for abelian groups, these things must themselves be prime numbers. Otherwise we cannot do it. And that is why a similar thing can also be, a similar argument can also be given for 15, because 6 is 2 times 3. Here also you will get 2 distinct primes, 3 and 5. So just like this, you can also not have any integral domain with 15 elements. What about 4? For 4, of course, this method does not work, and in fact the result is also not true. And in fact there is an integral domain, at least one integral domain of order 4, which is this. I know this it looks all messed up and very unorderly, but you understand what I was trying to say. So the solution would look like this. Let me just once again briefly go through these steps. So what you first do, you first suppose that okay, there is an integral domain D with 6 elements. Then you concentrate on this additive group D. Now because the integral domain has 6 elements, from one of the corollaries to Lagrange's theorem, you get this for all x belonging to D. Fine. This equation implies that the characteristic of D divides 6. This divisibility relation, along with the fact that the characteristic of D must be a prime number, implies that this is either 2 or 3. But then, as we have seen, you can, in each of these 2 cases, you can take the help of Cauchy's theorem for abelian groups to get an element which will ultimately give you a contradiction. So that is why this itself is not possible in the first place. And a similar thing works for 15 also. There the roles of 2 and 3 will be played by 3 and 5, not in any particular order. And this is an integral domain with 4 elements. You just verify it yourself, okay? Instead of writing, should I write for, okay, let me just show it as 4 elements. And the operations are addition and multiplication in the ring Z2 X. It is a very easy and a routine matter to check that this is an integral domain. You just have to keep in mind that the coefficients of these polynomials are 0 or 1, each coefficient. That's because they are coming from this field Z2, which has only two elements, 0 and 1. So what do you have to show to prove this? First, you show that this is the subring of this, which you can just simply verify by considering the differences and the products that can possibly be formed from these four elements. Show that the set is closed under both of them, so then it will be a subring. And it also of course contains the unity of this ring, which is the element 1 from Z2. What else? This does not have any zero divisor because the original ring itself is an integral domain. So it does not have any zero divisor. So that's why it is an integral domain, and you can see it has precisely 4 elements. So that settles the 4 elements part. And finally, use these observations to suggest a result about the number of elements in a finite integral domain. Do you see that the result fails for 4, but it holds for 6 and 15? How are 6 and 15 different from 4? Besides being different things, different integers, they are different, and at the same time these two are similar because they are divisible by distinct primes, at least 2 different primes. 2 has the prime divisors 2 and 3, 15 has the prime divisors 3 and 5. 4, however, has only one prime divisor, 2. In other words, 4 is a power of a single prime, but these are not. And this is what determines whether these can be orders of a finite integral domain or not. These cannot be. And you can now clearly see that in fact if you are given a general integer n and it is said, it is given that there are distinct prime divisors p and q of n, you can just carry out a similar argument for to show that no integral domain with exactly n elements can exist. However, we are not saying anything about integral domains having prime power orders, that for every such number there is an integral domain having that number as order. We are not saying anything like that. We are just simply saying that for this type of numbers which are not powers of a single prime, no integral domain with exactly that many elements can exist. So that is your final conclusion, and there this solution ends. And here the video also ends. So if you have something to say about these things, you can use the comment section below, or you can of course mail me. My address, like usual, will be the link will be there in the description. And tomorrow we have analysis, where I think last Sunday I wrongly said that after finishing the chapter on infinite series, the next thing we have to do is continuous functions. But before that we have a very heavy chapter that on infinite sets. So that comes next. So tomorrow we are going to start that, and then we will see what comes next. So with that I wrap things up. Yeah, so that's just it. What more can I say? There is nothing else to say. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.